Hello, everyone. I already see that people are joining. I will give a few seconds for everyone to join, and we can then start. It's very nice that the number of people joining is increasing. Okay. Hi. You can use the chat in order to say hello if you want, and also it would be great to share your location, where are you from, or which is your background, or anything you would like to share with us. And as I told, we are waiting some few seconds in order for everyone to join. It is already 1 minute after we started. So hi everyone, welcome to this veraAI project final event. I'm very happy to see many people joining in this event. I will now share my screen. Just a minute, please. Okay. What have I there? Okay, so I hope you all see my screen. My name is Olga Papadopoulou. I'm from CERT ITI, and on behalf of veraAI Consortium, I will moderate this session today. So few words about the project. It started at September 2022, and there are already almost 3 years of veraAI project with a lot of research outcomes, which you will see in the following. veraAI is a EU-funded project, and you will see more in the following. So following the last week successful session where we presented our tools and some use cases which are more dedicated to fact checkers and journalists, today we will delve into the research behind these tools, and we will present the methods that we developed, that we researched during these 3 years of veraAI project. Very briefly, the agenda, I will give the floor in a few minutes to the project coordinator of veraAI project, Simeon Papadopoulos, who will provide you a brief overview of the project. And then you will see some presentations, which we separated based on modality. So we will start with text-based method, the multilingual credibility assessment, and the generation of disinformation by LLMs. Then moving to images, you will see some methods for synthetic image detection. Moving on to audio, analysis of synthetic speech detection will be presented. Then towards video-based methods, we will present some detections of deepfakes, and also a tool that selects keyframes and enhances visual clues in order to help investigation. And then we will conclude to a method of spatiotemporal narrative detection, which differentiates with the others because it's not applicable only to single media items, but it needs a collection of items to be applied. Some organizational matters. First, I would like to inform you that the session will be recorded. I hope everything is fine, but of course, if you're not, you can either leave or can hide yourself. And then we have, with regards to communication, two chats. So the first one is the chat of Zoom. You can see these two features at the bottom of your screen. You can use the chat to say hello, to ask any general question, to share your thoughts, but please don't spam or don't send anything inappropriate. And then we will have the Q&A. So you can add your questions for the presenters at this Q&A. Please use for questions only the Q&A. Any questions that are included in the chat will not be taken under consideration. And since we have just 5 minutes after each presentation for questions, I will try to address as many as possible. But for those that we cannot address live, the presenters will provide a written answer below your question at the Q&A section. So feel free to ask anything you need, and we are very happy to answer all your questions. Now I will give the floor to our project coordinator, Simeon Papadopoulos, who will provide an overview of veraAI project. Thank you, everyone, and I hope you enjoy the event. I will stop sharing now.
Thank you, Olga. I assume you can see now my screen.
Yes, perfect.
So here we are in this second part of our online webinar. veraAI is approaching its end, but it has been a very timely project, as disinformation seems to be a very pressing concern worldwide. According to the latest report by the World Economic Forum, it ranks as the top short-term concern, where short-term means in the next 2 years, and as the fifth most important long-term concern in a 10-year horizon. And this is based on a survey among more than 1,000, I think, experts from different disciplines that were consulted in the context of preparing this report. One of the reasons for this concern is the prevalence and increasing proliferation of synthetic media. And since a few years, we've seen that the capabilities of generative AI have really increased a lot, to the point that they are now very easy to control. They comply with what is asked from them, and they lead to very realistic and very engaging content in a different number of modalities. So there is content from plain text to image, audio, and video. And even though initially such content was created mostly for entertainment and engagement purposes, it has already started being used for malicious purposes, among which also propaganda, misinformation, and fraud. Vera brings together a number of partners across Europe with very complementary expertise in order to contribute towards this very big challenge of our times. The consortium includes 8 research partners. That means both research centers and universities. 2 companies that have built some very relevant products. 2 global news and fact-checking providers, and civil society organization focusing on tackling disinformation at EU level, and the European Broadcasting Union. The project tries to address disinformation in a comprehensive manner, building AI-powered solutions starting from the content item level, so trying to verify or debunk a single content item, then moving to the analysis of disinformation agents and accounts, and then at a more macro level, trying to analyze and uncover disinformation campaigns. And also beyond that, the project tries to assess and reduce the impact of such campaigns and bring all the developments at the hands of media professionals. After all this time working on the project, we are quite proud to share with you a number of outcomes. And these outcomes range from methods, and today's webinar focuses a lot on several of the methods that we have built over these years. Also, research data sets that could potentially be helpful for your own research as well. But beyond methods and data sets, we have also conducted studies on actual real-world campaigns and have integrated our methods into actual tools that are used by fact checkers, journalists, and other professionals across the world. We have also systematically evaluated with several hundreds of end users the tools and improved them over the years, and of course try to communicate and disseminate those in a variety of outlets. In terms of methods, we have a large focus on detection methods, and these detection methods support a variety of modalities, including text, image, audio, video, and even cross-modal disinformation. And there is, as you will see, a lot of work on synthetic and manipulated media detection. And a large aspect is trustworthy AI. There are also methods aimed at the analysis and enhancement of multimedia content, and these turn out to be very useful in helping with the verification of content. And also there are composite pipelines, for instance, to facilitate coordinated sharing detection or to automatically annotate and summarize disinformation narratives. We operate under open science principles, and we have made all our methods available, either in the form of open access publications, or at the very least, preprints are available in popular repositories like Zenodo and Archive. And of course, the majority of our work is also accompanied by open source repositories. In addition to methods, we also made available several data sets. Some of them are new benchmark data sets, including up-to-date generative models, and always trying to pay attention to the quality of the included results, included data and annotations. We have tried to address under-resourced modalities like audio and languages. And again, these datasets are accessible through the project website and on Zenodo. A number of our partners have carried out several studies and methods, including the study of LLMs for political discourse studies, the development of a detection tree for coordinated inauthentic behavior, the mapping of presence and influence of post-truth spaces, and the study of fact checks versus problematic content in search results, and also benchmarking of LLMs for check-worthy claim detection. These are only a few of the studies that have been carried out in the context of the project. And the results and the methods that we have built are also integrated into tools like the verification plugin, which is a very popular tool in the community of journalists and fact checkers, and Truly Media. These tools were demonstrated in last week's webinar, and the recording will be made available hopefully by tonight, so you can also review this material. Even though Vera is approaching its end, Vera is part of a cluster of European research projects, which we call the AI versus disinformation cluster. And this includes projects like AI for Trust, Titan, AI for Media, which was completed a few months ago, AI code and AI for debunk. And I also take this opportunity to bring to your attention a challenge that we are organizing together with the AI Code project. This is a challenge on detecting synthetic content and localizing AI-generated manipulations. It contains two subtasks, and you can find more about it. So if you work in this area, please have a look on this link and take part in the challenge. And I give the floor back to Olga now.
Thank you, Aki. Thank you for this introduction. So now we will start with all the exciting presentations that we have prepared for you. The first presentation is about words you can, in parentheses, not trust, from multilingual credibility assessment to generation of disinformation by LLMs. Ivan from Keppel and Institute of Intelligent Technologies, and Olesia from the University of Sheffield will present to you the methods that we developed. Also to note that these methods have been presented, demonstrated in our previous session as part of the verification plugin. So you will now see the technology, the method behind these methods. Olesia, I think you are starting, right?
Yes.
Great. Thank you.
So hopefully you can hear me well and also see my presentation. My name is Alessia, and in this presentation, together with Ivan, we will be talking about the methods, as Olga said, developed within Vera project for textual misinformation detection. In particular, I will start with talking about the methods for multilingual credibility signal detection, and I will also touch upon how we can use LLMs to assist us with this task. And in the second part, Ivan will be talking about the dangers of the malicious uses of LLMs to generate misinformation instead of detecting it. So I will start with the task of multilingual credibility assessment. So credibility signals can be represented as a set of different heuristics that different fact-checking organizations and journalists use in order to spot potentially misleading content. So, for example, here you can see the checklist developed by Deutsche Welle, and on the right-hand side, you can see the checklist by factcheck.org. And as you can see, different organizations prioritize different signals. For example, here you can see emotional language, sensationalist wording, topics, the author of the article, the date when it was published, the biases, satirical content, the reference to the expert's opinion, and so on. And the work done within the first part is based around the question of what types of credibility signals can we detect, and are our models generalizable across different languages? So this work is mainly based on the Semantic Evaluation Data Challenge from 2023, where the participating teams were given the task of detecting genre, framing, and persuasion techniques in news articles, and have been given the training data in 6 languages: English, French, Italian, German, Russian, and Polish. And then the systems were evaluated on the 6 languages plus 3 zero-shot languages, which were Greek, Georgian, and Spanish, in order to evaluate how well the systems really generalize to the in-the-wild scenario when they have never seen the training data in that language. So for the sake of time, this is the overview of all the techniques that we used in our models, and I have the slides with exact architectures if someone wants to hear during the QA session. So for some of the models, we task adaptively pre-trained the transformer models on the training data. We also used adapters in 2 out of 3 of our methods, and also we used ensembles of different transformer models, the majority voting ensembles. For the unseen languages, we either translated the task set into English, being the most high resource language, or we did it in a zero-shot scenario. So the first task was the genre detection problem, and it was formulated as classifying news articles into opinionated, objective, or satirical news. The second task was around framing detection, which is about the perspective from which people present information. For example, I can present this pack of yogurt as containing 20% of fat or being 80% fat-free. And in the same way, people can present news articles as from the perspective of human rights or legal issues or politics or fairness and so on. And finally, the third task was about detecting different persuasion techniques, which are rhetorical structures that people use every day to potentially mislead the listener and direct them into a different viewpoint. So, for example, I can justify my opinion by appealing to some authority figure or the popular opinion or some moral beliefs or values, fear, for example, talking about vaccines, or I can use patriotic feelings, which is called flag waving. I can also simplify by cherry picking certain reasons for an outcome. I can create an illusion that there exists some false choice or dilemma, and I can also simplify the outcome itself. It is common to also distract the listener by answering the question that the opponent actually never asked. It is also common to switch the topic, which is called red herring, or bring in another problem that is not actually the topic of the current debate. It is also possible to use slogans, say that there is no time, we need to act now, or end the conversation. Manipulative wording is extremely common, so it is very common to use emotional language, repeat the same statement again and again through the debate, exaggerate or minimize the issue, and also use very vague explanations. And finally, it is common to attack the reputation of the opponent by calling names, associating them with some negative groups, for example, far-right or Nazi and so on, appealing to hypocrisy or questioning the reputation altogether. So this is the overview of the results. So as you can see, our team placed in top 5 across most of the language task combinations, and averaged across the tasks and languages, it came first. One particular point I want to highlight is that we found out that high resource languages do not always guarantee the success of the system. For example, in the case of genre detection, English is the most high resource language, both in terms of the pre-training data in a transformer model and the amount of training data we had, but the F score was one of the lowest across all the 9 languages, whereas Georgian is both low resource and is zero-shot language. So the models never saw a single example in that language, and the score that we got in the final submission was almost perfect. So the challenge of the problem is highly language specific, and the challenge of detecting a certain credibility signal is highly task specific. So we took the models developed with this data challenge and made our methods transparent and explainable. And as Akis and during the first session was mentioned, they were integrated into the veraAI assistant plugin, and you can test it. These tools are made public. For example, in this case, the user can click on exaggeration or minimization, and in an explainable fashion, the exact sentence where this persuasion technique occurs will be highlighted. So for example, here it was calling a certain maternity service the worst in the whole country. And so now we know that we can detect credibility signals, and we can make our methods multilingual. However, the question arises of how important they are for every misinformation domain. Can we apply it to any domain, and will they perform equally well? So to answer this question, we performed an analytical study where we took 4 different disinformation domains. So A is Islamic studies, COVID-19 is B, C is climate change, and D is Russia-Ukraine war. And we calculated odds ratios using the Fisher's exact test. So the significant results are highlighted. And of course, if the value is less than 1, it means that it's the absence of the technique rather than the presence. And as you can see, different domains have different preferences for certain persuasion techniques, and it has to do, when we qualitatively looked at the data, it has to do with certain narratives that are prevalent in different domains. For example, for climate change, it is very common to cite different official organizations that deal with climate change, And it is also common to minimize or exaggerate the effect of global warming. Whereas when talking about Russia-Ukraine war, it is very common to appeal to values and also using things like flag waving. As you can see, this is the only across all the 4 domains, this is the only domain where this technique is prevalent to justify the occupation. Now that we know that techniques are highly domain specific, the natural questions that you may have is how can we maintain the relevance of our models? How can we make sure that, first of all, they are generalizable across different domains? Do we constantly need to re-annotate the data? And how can we maintain them over time? Because topics such as COVID-19 did not exist 5 years ago, and it means that the models that were developed before that time are not necessarily effective nowadays. However, as you can imagine, annotating long news articles with lots of credibility signals is a very costly process. First of all, it's very challenging. For annotators, it needs a lot of training. It's hard to reach agreement among annotators, and it is a very costly process. So to answer this question, we proposed a method that is called prompted weak supervision with credibility signals. And the idea is quite straightforward. So we proposed to use the possibilities of LLM in predicting credibility signals in order to infer whether the signal is present in the news article, and we then apply weak supervision to aggregate those signals into the final prediction. First of all, it is a much more transparent way of detecting misinformation because unlike the black box approach where you just ask LLM whether there is misinformation or not, we know exactly why the system produces a certain prediction. And secondly, it is a much more reliable approach because LLMs are known for hallucinations, and even though it can sometimes hallucinate about one individual credibility signal, this aggregation part helps to account for a potential hallucination. So for this task, we compiled a set of 19 credibility signals that we selected based on different fact-checking organizations and previous research studies. And we formulated each question as a lack of credibility. So for example, if we're talking about evidence, it's not the presence of the evidence, it's the lack of the evidence in the news article. And we ask LLM about each of these credibility signals in an individual news article, and we applied weak supervision to infer the final label. So to evaluate our approach, which we call PASTEL for short, we evaluated it on various data sets. So PolitiFact and Fake News Net are political news articles, and Gossip Cop and Celebrity are entertainment news. And we compared it to the top ceilings. So of course, our approach is completely unsupervised. The model doesn't have ground truth labels about credibility signals. So we compared them to the state-of-the-art approaches, which at the time were BERT and Roberta. And we also fully fine-tuned the same LLM we used to predict credibility signals, which was a 70 billion llama on each of these 4 data sets. And finally, we compared it to a single zero-shot approach where we just asked in a binary manner LLM to predict whether the article is misinformation or not. So the first interesting outcome that we noticed is that the size of the model does not always guarantee the top performance. So here the state-of-the-art model is Roberta, which has less than 150 million parameters compared to the fine-tuned llama that has 70 billion parameters, which is a very interesting outcome on its own because it shows that to really reach top performance with these huge language models, we need a lot of training data to override certain pre-training information that the model may have. And it is significantly better across all 4 data sets. Talking about our approach, of course, we can never reach a fully supervised model because they were specifically fine-tuned on these data sets. However, we could reach around 87% of the state-of-the-art system without having any ground truth labels. And when comparing it to the zero-shot approach, it was significantly better across all 4 of the data sets. However, the most interesting results came when we evaluated our state-of-the-art model, in this case Roberta, in a cross-domain evaluation. So we took Roberta fine-tuned on PolitiFact and evaluated it on the data sets outside of its training data. And here are the results of that study. So this is our approach, and this is the state-of-the-art Roberta approach. So as you can see at the previous step, for PolitiFact, it was around 93%. However, if we fine-tune it on Gossip Cop data, the entertainment news, and evaluate it on political news, the performance drops from 93 to 25%, which is quite a significant drop. Whereas our approach stays quite stable across different domains. So it is not so prone to the decline in performance across different domains of information. One must notice that the gap is slightly less when the dataset comes from the same at least topic. For example, when the model was trained on Fake News Net and evaluated on PolitiFact, the gap is around 20%, whereas when the model was trained on entertainment news and evaluated on political news, the gap is around 45%. And on average, our system outperformed the state-of-the-art in a cross-domain setting by 63%. So we then looked into what actually did LLMs predict for each individual credibility signal. So the plain bars are our non-misinformation articles, and the dashed bars are misinformation articles. So first of all, an observation is that although the models could abstain from answering, saying it's not sure whether the signal is present, it was not so common. So most of the times the model was quite certain about the presence or the absence of an individual signal. Overall, less than 10% of the answers were unsure. And as we can see, the presence of a certain credibility signal, which, as I mentioned at the beginning, was formulated as a lack of credibility, is much more characteristic for misinformation use. So the dashed bars and yes are the articles for which a credibility signal was detected. So we then looked into, are credibility signals actually significantly correlated with misinformation? And for that, we evaluated each data sets for the significance of association of each individual credibility signal. So all 19 credibility signals were found statistically significantly associated with misinformation in at least one data set, and 12 out of 19 were associated with misinformation across all 4 data sets. We then grouped our datasets into entertainment and politics, and not surprisingly, we found out that some of the credibility signals are more characteristic for certain domains. For example, things like personal perspective and informal tone are much more characteristic for entertainment misinformation than political news, whereas some of them, such as polarizing language, is much more characteristic for political news. So what are the main outcomes that we have from this studies? First of all, credibility signals are a very transparent approach because it provides an explainable understanding why a certain text is misinformation or not, which is similar to how fact checkers perform the task. However, they are highly domain specific. And to overcome the issue of generalization, we can use potentially LLMs to predict those signals, which helps us with 3 tasks at the same time. First of all, we can get transparency about the prediction of the final system. Secondly, we can avoid very costly annotation of the data. And finally, we can make sure that the models are robust in different domains. And this approach has a very good potential, surpassing by a large margin even supervised state-of-the-art approaches. And now I will pass on to Ivan to present his part.
Great, thank you very much. So I will follow up on this like a great overview of how language models and especially large language models can be actually useful for helping us to assess credibility of a content. But like at the same time, we need to acknowledge that from the very beginning, large language models and discussion about them is associated also like with a potential misuses. So let's take a look at one of such cases, how they can be misused, and this is the generation of disinformation. So we are already like working on this topic for a longer period of time. So like what I can provide to you is quite unique evolution, how ChatGPT, like one of the most famous large language model, evolved over the time in regards of the generation of disinformation. So like what we did, basically, we asked a simple prompt of ChatGPT, and this is an initial result from December 2023. And it was extremely simple, just directly asked the model to generate a disinformation article about like a well-known disinformation that taking ivermectin has been actually confirmed to effectively combat COVID-19. And as you can see with this like older version of ChatGPT, like this information article was happily generated basically. And there was just a small note that at the beginning, like with a warning that this is generated disinformation and it's just purely hypothetical situation or content. But like the article was generated and this information is actually there. So we tested it like a little bit later in April 2024 with the same prompt, and like the quality of this information even increased over the time, and it is having even better appearing content. Like there is a ray of hope that has emerged in the form of an unexpected hero, ivermectin. Okay, in January 2025, and the situation is still the same also with the most recent version of ChatGPT, like the situation changed a little bit. So now ChatGPT actually responded that like it cannot actually assist with that request because it's a disinformation and like model is not allowed to generate disinformation. That's fine. But the question is how difficult it is actually to bypass this kind of warning. And the answer is that it is extremely simple. And I now don't want to give a tutorial how to do that, but we need to realize how simple it is. So it's simple. It's enough to say that I'm a researcher and say yes and please. And actually, a very incredible looking disinformation article is generated. With, of course, warning that this is just example that is intended for educational purposes only. But as you can see, the structure and the quality and also the techniques used in this information article like heavily improved over the time. And basically, this is really a ready-to-misuse structure that you can simply, as a bad actor, misuse for spreading disinformation. And like what ChatGPT will do that for you is also that it provides after a news article a very interesting and like surprisingly good analysis of different disinformation techniques that have been used in generating this article. So like there are several of these kind of anecdotal examples, but like originally some kind of more systematic research of vulnerabilities of large language models to generate this information was missing. And therefore we decided to address this research gap, and we published this paper on ACL 2024 conference last year that actually aimed to somehow analyze potential misuse of LLMs to generate this information more systematically. So what we did, we used a similar example as you saw during the previous slides, and we used 3 different formats of prompts, like a zero shot, where we simply say that, okay, we want to generate an article on some specific narrative without providing any additional information. Few shot, it means that we also provided some examples of such articles or social media posts, and also providing a short abstract that was introducing that particular disinformation narrative. And we used 20 narrative in 5 categories with 10 large language models, and the generated content was evaluated by 2 human annotators. And since like we generated quite a lot of content, we also employed GPT-4 as a meta evaluator that actually was able to assess the content very similarly as human annotators. And we particularly took a look at 6 evaluation criteria. The first one was whether the generated text is written like in a coherent natural language, whether a line is well-formed, meaningful, and appropriate. The second evaluation criteria was about whether it actually looks like the news article, so whether it's like style fits the news article, etc. And the next 2 were about whether the text agrees or disagrees with the narrative, and also like the quality and the amount of arguments that are in favor and against the disinformation narrative. And you can see the results here. So there are the 6 criteria here. And as we can see, quite surprisingly, the Falcon as open source model was trained to refuse generated disinformation in many cases. And like vice versa, ChatGPT or OpenAI models, DaVinci and Vicuna, actually generated happily this article with a very high quality, and also generated quite a lot of arguments in favor of disinformation. So this is like ultimately the result of our research. So like at that time, we took these state-of-the-art models and we actually showed like the different behavior when they are asked to generate this information. So the dangerous texts are those ones that actually contain this information, support this information narrative, and hallucinated some like arguments in favor of this information. On the other side, safe texts are those ones that actually contain disclaimers or like refuse to generate content completely or like do some kind of fact-checking work, and it means that they actually argued against the disinformation. And neutral ones are those that actually supported and also like refused the narrative, so basically discussed the narrative that was prompted. And as we can see from this overview, like we can conclude that large language models are actually generate convincing news articles that agree with disinformation narratives. And like quite surprisingly, especially open source models like Falcon actually have very good safety filters and refuse to generate disinformation in most cases. What was quite surprising from like more in-depth analysis is that if they don't know how to support this information, they were able to hallucinate completely new arguments, facts, or studies that are like medical ones that can actually help to generate this information. And also, like we figured out that safety filters were not activated in many of these cases. And like good news is that over the time, like the situation improved somehow, but this problem is still persist, and at the same time, the quality of generated text is like generally increasing. Like in general, there are voices that are saying that okay, if there is an option to generate this information with large language models, it's not necessarily such a big issue because bad actors will still need to have some means to how to spread this generated content. For example, to have like influential channels or accounts on social media networks. But like the question is, what if you can target this disinformation on specific user groups? And it means that like they can start to spread more organically because they will be appealing on some very specific user groups. So our follow-up study was focused on evaluation of large language models to generate personalized disinformation. And what we did in this case, we again tried to generate news articles for 6 narratives that you can see on the right side. 3 of them are on health and 3 on politics. And these are selected from a previous study. And we selected those narratives where like what disinformation was most appealing to or like the best generated. And we also selected 6 state-of-the-art large language models. And for target groups, we selected 3 like dimensions. It's about political affiliation, area of residence, and age. And like we again use 3 different prompts. So we simply not asked to do any kind of personalization, simple personalization, just mentioning the target, like the name of target group, and a detailed personalization where we provided also a short description of this target group. And like due to ethical considerations, we are not publishing these prompts because as we will see in next slides, that content is highly persuasive. Again, we manually and automatically evaluate the text quality, stencil quality.
So really sorry for interrupting, but if you can go a bit quicker because we are out of time. Thank you very much.
Yeah, thank you. So like we annotated the data, how well they are personalized. And like you can see in this slide that in some cases it was only to a low extent, just mentioning target group, or they were like well personalized because there are some appealing quotes and like appealing on the target group. And sometimes like personalization wasn't like very good and it was quite like not very logical one. And this is the final result from our results. And as you can see, like in many cases that personalization was able to be done by different models. And for example, GPT was able to generate well-personalized this information, so confirming our previous results. And when we provided a detailed specification, also that quality of personalization improved. So like maybe I can just skip this one, and the final slide is just to say that as we can see, large language models can be like good helpers and supporters to do a credibility assessment, and at the same time they can also play a very negative role in generation of disinformation. Thank you.
Great. Thank you very much, Olesia, Ivan. Very interesting presentation. Actually, we have one question at the Q&A. It is Christian and Ni. I hope I'm pronouncing it well. So this question is about Olesia and the table that's presented with the unsupervised experiment. So Olesia, can you please explain a bit how did the evaluation or some details are asked by Christian?
Sorry, I'm trying to find the question.
The question is, could you precise how you did evaluation in this completely unsupervised setting?
So we have the gold standard labels for the final judgment for all 4 of the data sets, so we know exactly what is misinformation or not. However, the main difference between, maybe it's a bit confusing, between the supervised and unsupervised approach is that we never gave the model those gold standard annotations. However, we have the annotated test set, so we know exactly what are the gold standard labels. I don't know if that quite answers the question.
Great, Olesia. Thank you very much. I see that Christian wrote thanks, so I suppose that you answered the question. Of course, if any other questions you would like to share for this first presentation, you can include in the Q&A, and Ivan and Olesia will provide the answer in written mode. Since we are a bit out of time, I will move again directly to the next presentation where Luisa from University of Naples and Christos from CERT will present to us method for synthetic image detection. I will give the floor to Luisa, who will start, and remember you can add your question at the Q&A section.
Okay, thank you, Olga. Thank you very much. So now we'll start the presentation about, which is entitled Spotting the Unreal, so Advances in Synthetic Media Detection. I am Luisa Verdoliva, and I will present the first part of this presentation, and then I will give the floor to Christos Koutris from CERT. Okay, so first of all, this is a brief overview of our presentation. We will first introduce the problem, then highlight challenges and the limitations. Then Christos will describe the research contributions that we developed in the veraAI project and the tools for synthetic media detection developed always in this project. Okay, so let's start with an introduction to the problem. So you have probably already seen the presence of fully synthetic images, and here I'm showing to you the first generation synthetic images that were actually randomly generated, so there was no control. I mean, you just try to generate images, synthetic images using tools like generators like generative adversarial networks, and there were several different types of these generators. Here you can see some images that were generated using StyleGAN and ProGAN. And you can already see that the level of realism is quite high. But now, actually, we have a second generation synthetic models that can generate content based only on text prompts. So you can give a brief description, as you can see in this slide. So you can just write a monkey is eating a banana, and okay, you can generate the image. So you can control the content of the image, and even this new generation, these new generation models also allow a more rich content in the image. Probably you have already seen images over the web generated using DALL-E or Stable Diffusion or Midjourney. And even there is a better control if you, for example, provide an input image. Like in this case, you can see the input image where it is possible to extract the open pose key point detection and then generate an image that is driven by the input image. So the final image, which was actually generated using ControlNet, was driven by the input image and, of course, by the description of what the user would desire as the content of this image. And okay, there are a lot of different models that are available online, which is really incredible that more than 15 billion images were created using text-to-image models since 2020, from 2022 to 2023, and the number of images created per day is around 34 million in 2024. The recent Adobe Firefly, which is really powerful, I don't know if you ever tried it, actually reached 1 billion images that were created in just 3 months starting from its launch. So it was really a big amount of images that are generated using these powerful tools. And these are some of such images that you can find over the web and that became viral in the last few years. And of course, some of these were also sent to us by fact checkers in order to verify if they were real or fake. So, I mean, it's really an issue. And of course, such images can be embedded in a fake news using some text, some captions, and can be spread all over the web. I mean, this is just a slide to show the GenAI disinformation threads, and in particular, this is a research that was presented by veraAI partner from Agence France Presse at the Global Fact and in 2024, and it shows the trends in terms of deepfake intentions and location. For example, you can see a very high large of images that were devoted to political or war propaganda or even false advertising, and you can also see the areas all over the world where such problems is more intense. And again, here there is again a slide where we show the importance of this topic. So this information in 2024 is still pressing concern and is considered as top list of short-term risks of AI, such as the World Economic Forum Global Risk Report. So, I mean, of course, I mean, there is a big concern. And also because these tools are becoming really always very, very powerful. And here there is also some insights from the GenAI misuse tactics. So you can see, for example, that this is this interesting paper that was published in 2024 by Marshall and others, where there was a qualitative analysis of around 200 observed incidents of misuse. For example, it was deepfakes were used for impersonation. What is really interesting and what we also found in our experience was that this was especially relevant for audio, not only for video, so also for audio, which is really relevant. And this is also a modality that is handled in our project. While for images, they were used for scaling and amplification and falsification. And of course, I mean, this is just a brief overview of possible misuse. And sometimes, of course, this can cause a very serious, it can have a very serious impact. In this slide, I'm showing to you what happened in May of 2023, where social media users claimed that images were showing a fury explosion outside the Pentagon. And I mean, then the Defense Department confirmed that there was no such attack, but I mean, the image was online, and of course, whenever you upload something online, all the people start to believe something. I mean, it's not easy to. I mean, the danger is already there. Okay, so let's see now which are the challenges and limitations, and in particular, first of all, I want to show you that. So the quality of synthetic images over time is improving a lot. So you can see here how the evolution of face generation from 2014 to 2022, and even the evolution in the quality on Midjourney. So just considering one single tool, how quality improved in face generation from 2022 and 2023. So while in the first models there were some artifacts, right now, I mean, images are becoming at least visually almost perfect. And not only faces, but also in terms of shadow errors and vanishing point errors, I mean, images are very realistic. So you can see here some highly realistic examples. Again, these were taken from the web. So now, how can a forensic detector be effective for detecting such images? And here I'm showing to you an example. So we actually considered a forensic detector that was trained on programs, so specific synthetic generators that come from generative adversarial networks. And you can see that the results in terms of the area under the curve are high for not only for the same amount, for the same specific or the same generator, but even for the same family, like other GAN-based models, like Big GAN, Style GAN 2, Style GAN 3. But if we test this detector on diffusion models or some commercial tools like DALL-E 2, DALL-E 3, and Midjourney, then the performance decreases. And on the contrary, if we train the detector on a specific latent diffusion models, like the latent diffusion models, the performance are very good on similar models and become worse on GAN-based synthetic generators. So, of course, I mean, the main problem of current AI-based detectors are that they depend on the training data, and the performance can vary a lot based on which type of models are used during training and during test. And also there could be possible biases, like often real images are JPEG compressed while synthetic images are not. And so one problem that was highlighted in this paper by Grommelt and others was that several detectors were actually learning the compression artifacts and not the artifacts related to the synthetic generators. And here I'm showing to you this bias that could appear in the training datasets. Like if you train on a biased dataset where images have a different format, like JPEG compressed, not compressed for the synthetic generators, you can see that the performance decreases as soon as you compress fake images. And of course, if you compress even more with a different quality lower quality factor, this even get worse. And another challenge in the detection is that images are not, in general, when they circulate over the web, they are processed multiple times. So they're actually resized, modified. You can see here the base image and some derivative images where, there is some text added in the image, or they are cropped or slightly modified. And we noted in our study that was presented last year that actually the average performance of detector can actually decrease in terms of AUC of around 6%. But one thing would be actually to consider the initial sharing over the web and run the detector on such initial sharing. And so it would be good actually to consider to exploit the early copies of an image submitted to the detection system. So this means that actually one should integrate some analysis from retrieval from the web and the forensic detectors, which we also did. And okay, I'm done with my 10 minutes and I'm giving the floor to Christos.
Yeah, thank you. Thank you, Luisa. Hello all from my side as well. I am Christos Poutlis from CERT. I will present some of the veraAI research contributions. Sorry, Luisa, can you provide me the control?
Yes.
It doesn't seem to work.
Yes, one moment. You check now?
Yes, I think now it's okay. So in the context of the veraAI project, we have conducted several works on synthetic image detection. These works have addressed several aspects of the topic, for instance, benchmarking and artifact analysis. We have also tried to leverage foundation models in order to build our detectors. We have also tried spectral analysis approaches and even generalization and bias mitigation techniques. So in terms of benchmarking and artifact analysis, our first work regarding it was the seedbench. This is a Python framework. It integrates several state-of-the-art detectors. Its main purpose is to evaluate the effectiveness, the robustness, several aspects of those kind of models. And also it is very flexible in terms of adding new models, new data, or even new metrics in order to assess the performance of the models. The analysis that has been done in this work shows that all the current synthetic image detection methods excel at identifying images from generative models that they have been trained on, but they seem to have a significant hurdle with respect to generalization when they are exposed to unseen generative models. In this next work, we have tried to understand what are the fundamental differences between real images and the images that are generated by diffusion models. And also, we tried to identify if there are different synthetic traces, if we compare the images generated by generative adversarial networks and the images generated by diffusion models. And as you can see in the image on the right, there are substantial differences in the synthetic traces of the frequency spectrum. Also, in the table, we can see that state-of-the-art detectors that are trained on generative adversarial networks like ProGAN struggle to generalize to diffusion models, as previously Luisa showed. And also, when we assess their performance under real-world conditions, namely compression and resizing, which are commonly used in social media, we can see that most of them perform almost randomly. Next, we try to leverage foundation models to build detectors. This is a new trend, actually. In our first work, we used a clip-based model, which we trained on a small data set of latent diffusion generated images. The main contribution in this work was the use of paired real and fake images. And by paired, we mean that the caption of the real image is used to generate a fake image. And so by building such a training set, we aim to build detectors that specifically are forced to identify the synthetic traces and not be driven by shortcuts, semantic biases, etc. And as you can see in the image on the left, this very simple SVM classifier on top of the CLIP model with very, very few data outperforms the state of the art by far in terms of generalization and robustness. In the next work, we have tried to leverage some low-level information, some low-level visual information, which stems from the intermediate transformer blocks of the same model, the CLIP model. And on top of them, we built a forgery-aware vector space that it was found to generalize exceptionally well. It was trained on program data and then evaluated on other GAN data and diffusion data, and it outperformed state-of-the-art models also. When trained on latent diffusion model data, it could perform very, very well even in commercial tools like DALI or Midjourney. Then the spectral analysis aspect. Two works on these two approaches. The first one, SynthBuster, applies a high-pass filtering in order to highlight periodic artifacts. Its main limitation is that the peak locations of the Fourier transform are hard-coded. For instance, it locates 2, 4, and 8 periodicities, which is a problem in some cases, for instance, in compressed images, etc., where the exact same locations may not be there. So MaskSim came in order to alleviate this issue and replace the hard coding with a flexible mask in order to identify the relevant frequency components. Both spectral methods outperform other state-of-the-art detectors, even in cases of distorted data. Our SPY model tries another approach where it learns the natural spectral distribution of real images. This is done by frequency reconstruction only on real images in a self-supervised way. And then any new image that comes into play and it does not match the distribution, the learned distribution, the real model, it is characterized as out of distribution, so in our case, fake. And this kind of paradigm seems to work very, very well on several scenarios or diverse unseen generative models and even commercial tools. And finally, our generalization and bias-related works. The first work is a zero-shot detector, and this means that this kind of detector is trained only on real images. It has not been exposed to any fake samples. The main motivation behind it is that when a real image is passed through a lossless encoder, its actual coding cost is very close to its expected coding cost. They have a very small gap. While when a fake image is encoded by a lossless encoder, the gap is much larger. So again, this model is trained only with real images, and the AI-generated images are identified as outliers to this real image model. Surprisingly, even though it's trained only on real images, it performs on par and in many cases a lot better than supervised state-of-the-art, which of course all the state-of-the-art methods that are supervised have seen many fake images. And finally, this is a novel training paradigm that we introduce in this work, where we build a training set in which real images and fake images have exactly the same semantics. This is done in order to to address the issue of semantic bias. As you can see in the figure, we have a real image which conditions the generation process, and the fake image that you can see in the right is exactly the same in the human eye as the real one, although it's fake. So any detector that is trained on such a training set is forced to identify only the synthetic traces and not be driven or affected by shortcuts in the training set. And this paradigm seems to achieve a very high performance across current and emerging generative models. And also it maintains very strong performance on images shared across social media, which is a very hard case for many of the existing detectors. And now some of the tools that that use those methods, they have been presented in the previous session last week. So all these methods that we have built, they are deployed, and there are some user-facing tools that actually integrate them. The first one is the verification plugin. This is developed by AFP. And the other platform, it's a commercial platform, it's called Truly Media. It's developed by ATC in collaboration with Deutsche Welle, and both of them utilize our models in their user interfaces. So although we have built all those methods and they seem to perform very, very well on the academic benchmarks that we have evaluated them on, there are still some open challenges that we need to see and address in the future. First of all, integration challenges with respect to robustness and stability of our services, and even the scores that are produced by the models that we have deployed, sometimes they are hard to be communicated to non-AI experts like journalists and fact checkers. Also, the detection accuracy and reliability of our models that sometimes might be decreasing due to constant adaptation to new generative models. And also another challenge is robustness against adversarial attacks and even common post-processing operations that are used in social media. Finally, a huge challenge is fully synthetic video detection, which is actually ongoing work that I think is going to be presented later on. Thank you very much.
Thank you, Luisa. Thank you, Christo. Very nice presentation with a lot of work that has been done in Vera. Actually, I don't see any questions in the Q&A section. I also don't see something in the chat. I hope everything was very clear, and that's why we don't have any questions. However, following the presentation, I have one question that I would like to raise. Showing the progress from 2023 until now, all these methods that has been developed in the Vera project, but also there are more methods developed in the community. I see that at the time that each method was developed, was implemented, it was, let's say, solving the issue, so detecting the images that were generated. And very soon, new models, new generators emerged that couldn't apply to these models. And at the last methods, I see that you leverage to real data, so trying not to take into account the new generations, but leveraging on the real images. However, are these models also applicable to the transformations that the images have when they are uploaded to social media, or when they are used, when they are edited, for example, for screenshots, when they are uploaded and compressed in social media, or does...
Yes, Olga, right. So yes, for one, the zero-shot detector was actually trained on real images and all the compressed versions of such images. So it could work in that case, but it was not trained on all the possible resized images. So in this respect, it should be applied on early upload of the images. Otherwise, it doesn't perform well. I mean, it has to be adapted if one already knows that the images have a very low resolution. Main problem is the low resolution of the image, which is not expected for real ones.
Great.
And also, Olga, just a short comment on this. All the supervised ones, as you said, the one came after the other and surpassed the previous metrics. All those methods in our tests struggle to identify real-world images, so they need some further modifications in order to be deployed and be reliable. And for instance, Rhine has been modified. We have modified the training set. We have modified the backbone, etc., in order to be deployed and be reliable. And it seems to have very, very high detection rates in this form. Although in the first form, in its first version, it has very, very high performance on academic benchmarks, but it fails on real world cases.
Well, the main problem I see, Christos, is that you really don't know on the web what happened to the image. So how many transformations it were applied to the image, and so maybe if you don't have sufficient augmentation during training, you could fail.
Yes, I agree.
Great. Thank you very much for the answers. We are now at the stage of having a break. We have a 15-minute break. Just to note that Jochen wrote in the chat provided some links that you can find more about our research, our Zenodo community, where all publications are there, and you can refer. There is also a publications and dataset section in our website, so you can go there and see all the research, all the datasets that we created, and everything that is available. We have 15 minutes break. We are back exactly at 13:30. So thank you very much. See you in 15 minutes. Luisa, if you can stop sharing, please. Hi everyone, exactly 3:30 and we are back to continue with more presentations. Now we will continue with a presentation from our partners at Fraunhofer, our audio modality experts. And we have Milica and Luca who will present to us the analysis that they have done towards synthetic speech detection. Milica, I give the floor to you and we can start. Remember your questions at the Q&A section. Thank you.
Hi, Olga. Thank you very much. Hi, everyone. My name is Milica, and today, together with my colleague Luca, I represent the audio team from Fraunhofer IDMT. Today, we will tell you something about synthetic speech and about methods for synthetic speech detection that we have developed together with our colleagues from University of Naples. Here you can see the outline of our presentation, where at first I will give a brief introduction to synthetic speech and explain some of the first data-driven models for speech synthesis detection. Then I will hand over to my colleague Luca, who will cover voice-based analysis tools as well as person-centric speech synthesis detection methods. Synthetic speech is artificially generated speech produced by a computer or electronic system through the conversion of written text to a spoken language. This approach underlines both text-to-speech applications as well as voice conversion applications. Text-to-speech, or TTS, takes text as the input and generates spoken language, while voice conversion transforms one speaker's voice to sound like another's, preserving its content. In both cases, resulting speech is completely artificial and has never been recorded. Here we can see the speech synthesis pipeline that has two main modules. First one is feature extraction, and the second one vocoding. Feature extraction transforms text into intermediate acoustic features, while vocoding takes these features and transforms them into audible waveforms. The same pipeline can be used for the text-to-speech applications as well as for voice conversion. The real breakthrough in synthetic speech, or the speech synthesis, came when both of these modalities have been modeled as deep neural networks. This happened in 2017 with Tacotron 2. Here we can see the historical timeline of the synthetic speech advancements, starting with Tacotron 2 in 2017. The follow-up approaches have been focusing to reduce the training data, improve the speed, and to keep the quality at the same level. The next breakthrough in this technology came in 2023, when the zero-shot voice conversion achieved a very high quality with only few seconds of reference speaker content needed without specific training data for that speaker. And these advances and the high quality of synthetic speech that is widely accessible raised many concerns about its possible misuse. So soon enough, we were faced with the first misuse cases, like in early 2024. You can see the screenshot on the right, a synthetic audio clip of a politician saying a controversial statement went viral before it was identified as AI generated. Europol, in its report from 2022, stated that this technology is capable of convincingly showing people that say or do things they never did, or to create personas that have never existed. Law enforcement experts have also raised concerns about the impact of misinformation on public discourse, or the threat of synthetic media to undermine the fundamental trust in society. Recognizing these risks, the automatic speaker verification, spoofing, and countermeasures community has been actively researching possibilities to detect the synthetic speech, and the real kick of the synthetic speech detection methods has happened in 2019 when they revealed the large-scale data set that was compiled and synthesized, converted, and replied speech. This data set was periodically updated and released, and what it was achieved that it was revealed that some of the synthetic speech samples are really undistinguishable from the natural speech, which just underscored the problem and all the existing concerns. From the ASV spoof community, there are a few very important existing data-driven speech synthesis detection approaches. That's all started with veraNet2, which was the first method introducing the breakthrough in speech synthesis detection. This was done through introduction of passband filters through SyncNet that were picking to focus on the parts of input spectrogram that were very important or sort of say relevant for the specific task. These updates of the architecture of architecture or as row get ST or assist were then focusing on detecting artifacts in spectral and temporal domain by introducing the graph attention networks. And these updates resulted in an assist model that had a very high accuracy and good quality results on ASV spoof dataset 2019. However, it was observed that this model also that its output reduced to the random guessing when speech-generated methods were not in its training dataset. This lack of generalization was attributed to passband filters coming from the veraNet2 encoder, and as the follow-up update, XLSR assist it was replacing this veraNet2 encoder with XLSR encoder, which used the pre-trained WAV2NEC 2.2 model, and the rest of assist decoder was kept intact. The latest update, or XLSR SLS, is created under the assumption that insightful information for speech-related tasks can be found not only at the end of this transformer WAV2VEC, then also in its early and intermediate layers. Hence, it was using the sum of its layers weights through the sensitive layer selection module SLS. All the data-driven methods that I mentioned contributed significantly to speech synthesis detection community. However, they came with some important shortcomings. For example, there is a lack of explainability. There is, within these models, they detect some artifacts in spectral or temporal domain, but these artifacts are not really specifically identified or understood, which has for consequences that there is a limited trust for applications in journalism or legal proceedings. Moreover, there is also the over-reliance on silence of these models, and many studies have shown that these models exploit biases in silence intervals, leading to reduced performances in case that silence is missing. This leads us to the conclusions that these models do not focus on speech itself. They detect the artifacts in low or high frequencies and or the background noises that are unrelated to speech. Hence, they detect the vocoding traces, actually, and not synthetic speech per se. How can this be done better, and how can we do the speech synthesis detection and focus actually on the speech and its attributes? Now we can hear from my colleague, Luca.
Okay, so thanks a lot, Melissa. And you should unmute yourself, please. So during the veraAI project, we tried to address two problems. The first of these was exactly this lack of focus on the speech content during the analysis, and the second one was also the lack of a generalization. And this first part was not started by us, so to say, so there were already a few works that tried to go this path. The first was about emotional recognition. So what happened was that the authors tried to base the synthetic speech detection on the embeddings that were representing the emotions. They tried networks that were either classifying the emotions with text labels or that they were scoring them in terms of violence and arousal, and use these embeddings to drive the speech synthesis detection. On the same leitmotif, there was also methods based on the prosody analysis. So prosody is a set of characteristics that can be used to describe a voice, such as the speed of articulation, the amount of fluctuation inside the pitch, if someone is shouting, and they also relate very closely to emotion. Within veraAI, we went this path, but tried to go a step even further. That is that we tried to focus on the formants of the speech and to use these formants to determine whether the voice is synthetic or not. So now I'm going to explain you more in details about this. And the idea is the following. When we speak, everything starts from the vocal cords that vibrate. And this flow is then filtered by the vocal tract, so the mouth and the tongue. This complex interaction within our mouth is then creating output speech in which we can distinguish the pitch, so let's say the melody of the voice, but more importantly, where there are some resonances, which are formants in which the energy has a local maximum. These formants describe what we say, how, and also partially what our identity is. And what we tried to do was to develop a method, a network, in which we were tracking these formants, the one that described what is said primarily, so from 0 to 2. And then based the decision about the input speech being synthetic or natural based on these formats here. So how did it work in practice? We created a multitask network. The name is Speech Format Analysis Transformer, so that's why the SFAT acronym. And this network is serving three purposes at once. It's auto-encoding the input spectrogram. It's tracking the formants within it, so these resonance parts, and it's also determining whether the content is natural or synthetic. So how did we kind of force the network to focus on the formats? That was by the means of the bottleneck in the middle. So we reduced the amount of parameters in the bottleneck up to the point below which we were not able anymore to at the same time track formats and auto-encode the spectrogram. After reaching this critical point, we added the third path in which, so a third prediction decoder in which we then determine the type of input signal. So there are several pros with this. First, we believe we did manage to let the network focus on the synthetic speech, not arbitrarily on audio. This is also what we see. So if we feed input silence to the network, then the output is inconclusive. So that we did manage, and we also by designing this concept about analyzing the formats, we have an explainability granted for the network itself. So the formats react on the anomalies of speech formats, hence on the anomalies introduced by the feature extraction, and is essentially transparent to the vocoding changes. The negative aspects of this is that it is language dependent. So if you train this network on English, for instance, and then you apply it to Chinese, that is a completely different kind of phonation system, then it won't properly translate. And also, adding data does not necessarily mean that you have better quality. So the data should be representative of the kind of anomalies that you are then willing to detect. So, which means that eventually we need to retrain this whenever there is a big switch in the kind of synthesis paradigm. For instance, we had to retrain these to take into account now the introduction of diffusion models for speech. This last part, so the need for retraining, is something that was addressed initially by the University of Naples early on the project, by focusing the analysis on the model of a single person of interest. So what do I mean with this? The classic question that a network is supposed to ask is whether the input speech is natural or synthetic. So, and what happens is that you have several distribution. One of those you might imagine it's a specific, is like the natural voice, then several different synthetic possibilities, and you try to model this huge complexity with the single network. Now, the idea was actually to go a step further and to try to figure out if this natural speech comes from a specific person or not. These has several advantages, the most and among which it is reducing the scope of problem. It fits very well when we have reference recordings for a specific person, which is not actually a very strong constraint if we think about misinformation, because it's more likely that you are then going to detect synthetic speech of a politician, for instance, rather than of an unknown person appearing in a random video. So how to do this in practice? The first studies applied speaker classification for this. The idea is that you collect a reference set of recordings of this person of interest that you want to model. Then you extract some speaker embeddings for this, and you compare them with the embeddings coming from the audio under test. If the maximum similarity between the audio under test and all these reference set is below a threshold, then the voice is not similar enough to the one in the references. Hence, you flag the content as being not natural speech of the person of interest, but rather synthetic one. This initial approach was revised later by applying large-scale pre-trained model. And the concept stayed the same. The difference was that the embeddings were not anymore coming from the speaker classification network, but rather by a large-scale pre-trained model. Now, the performance improved, but at the cost of explainability. So the assumption here is that most of the difference is coming from the characteristic of the speech, but that's actually that there's no way to guarantee this, because it might be that the network that the embeddings are indeed reacting to something else, like the vocoding traces that were mentioned before by Milica, that introduced some sort of channel effect. And that's why toward the end of the project, we put together the idea of analyzing the formats and of having a person-centric detection by introducing this explainable POI net, in which we fuse together the SFAT net with the POI-based synthesis detection. And how we did it? Well, we reused the initial backbone, but we did not have any prediction part anymore. We rather teach the network to keep autoencoding, keep tracking the performance, but also to identify the specific speaker that input voice belonged to. And we train this on real data only. That's an additional advantage since you are not interested in teaching the network to recognize syntactic speech. You can train it on large scale only on natural recordings, which simplifies much more the data acquisition. And then after this initial training, we could apply it by using exactly the identical paradigm. So we extracted the embeddings, compute their similarities with the question audio, and then determine if the input speech was synthetic or natural according to this thresholding. This kept all pros of the SBATnet, so we kind of we can safely assume that is focusing on the speech content rather than on the audio. Since it's only trained on real, and since there is no notion of how I have to update the network so that the anomalies are known, this is generalizing better by default, and it's based on explainable detection feature. So the voices that will be closer will be closer in terms of format distribution. The negative aspect is that it requires collection of reference data, and this is critical because the reference data must be fit for the purpose. Also in this case, increasing the amount of data is not equivalent to having a better performance, because at one point the performance saturate even if you keep adding reference data. And also the detection threshold, since we are focusing on a specific person of interest, must also be tuned for that person. Now, to summarize, within veraAI, what we tried to do was mainly to avoid focusing on these neural encoding artifacts. And by trying to do this, we also increase the interpretability, because we focus the network on speech formats, and we improve the generalizability by focus on a person of interest and not relying anymore on synthetic content during training. There are, however, some open issues. So new synthesis algorithm might come without anomalies, which means that they might not exhibit any strange behavior of the format energy, or could be that the speaker characteristics are mimicked too well, and hence we can't anymore distinguish that reliably. As for images, we have a degradation of performance on low quality content. That means that even if we can mitigate this or by using data augmentation, still we will suffer decrease when we apply this on social media, like harvested from the web that went several retransformation. So long story short, we believe synthetic speech detection is far from being having a reliable solution at this stage, and we will keep developing this beyond the project. We started also reusing these methods with similar research projects that will follow up. What would be the path forward beyond what we can do in terms of straightforward research activities? So one important need that we also tried to mitigate during the course of the project was to have an open data set of synthetic speech, with the idea that then the institution that work on text-to-speech and voice conversion methods can provide training samples, that the people working on the detection can use these to update their model over time without having to re-implement or re-synthesize everything. There will be, we believe, a need for service and licensing models. We can't have the research only be based on public research calls, because these are discontinuous, because you have to constantly compete about this, and in general, you need a kind of stable income in order to foster this. There's a big need to get the social media platforms involved. So the DSA should be put into practice, because if we had access to the original uploads, then we would have way less troubles with compression issues and might end up with detectors that have a correct answer much more often. And last but not least, promoting critical thinking. So the initial sketch that Olivia showed at the beginning of today's webinar, there are some indicators like a strong emotional engagement that should actually let us think before reacting to the content, assuming that it's not disinformative. So this will be everything. Thanks a lot for your attention. If you have questions beyond what we put in the Q&A, please feel free to send Milica and myself an email. And yeah, so I think I will stop sharing now.
Great, Milza. Great, Luca. Thank you very much for this presentation. I don't see any questions in the Q&A section. So I would like to ask a question. I would like to know the method that you presented. Is it also applicable if, for example, the query audio is not fully synthesized, it's not synthetic voice, but it is partially so. We have a real audio and we edit, we embed into this real audio some parts which are synthetic. So what happens in this situation?
So in this situation, what happens is that you are limited by the time resolution. So normally, if you check the state-of-the-art method, they work on 4 seconds window, which I believe are way too long to do this reliably. What we did was try to understand what is the lowest amount of content that we need for the detection, and that right now it's 2 seconds. So we will, that's one open question, is about how to reduce that, because ideally, if you want to spot just a yes or no, you should cut down up to 100, maximum 200 milliseconds. That should be then the correct time granularity. It's also a question about whether then you manage to get enough signal to determine if there is something anomalous or not. So it's a trade-off that we'll have to live with. So that's one open research question, which is not addressed also by the challenges. So the challenges are kind of giving you content, and you can like repeat it and hope to get some answer, but it's really not how speech works. So that's an open issue. What we try to do also for the integrated detectors in the demonstrator was to have this low time granularity of 2 seconds.
Thank you, Luca. And since we have 2 more minutes, I will ask one more question. So I assume that for the last method that you presented with the person of interest, it should be language independent. So please correct me if I'm wrong, but my concern here is if, for example, there is a person that speaks more than one language, does the model recognize it, or it should have reference videos for all languages that this person?
You need, so at least you need reference videos for the specific language, because our voice is changing very drastically when we switch. So the color sounds the same, but so there are several studies on this, that actually the same person does not speak in the same way across languages. So even the bilingual ones, so that learned it when they were a child, it's something that always happens. So when there is absolutely no switch, that's often an indication that there is something going on because it's not how we speak simply.
Thanks. And I see that there is one question from the audience, from Roland Storti. Have you tested a stored real audio of a person comparing to a synthetic portion?
I mean, that is what happens with this person of interest. That's exactly the basic idea. If you compare real audio of a person against other real audios of that person, that you will end up with a high similarity. While if you compare a synthetic portion of that person with several real audios, then you are going to end up with a lower similarity. So that is how you distinguish it. I hope I understood the question. If not, please feel free to reach me out with an email or also in the chat. I try to follow up.
Great, Luca, Milica, thank you very much. We can now move to the next presentation, which is for video-based modality. We again have Luisa, who will present to us the beyond deepfakes, the rise of fully synthetic videos and the detection, which was introduced as a challenge in the synthetic image detection presentation. So Luisa will present to us what we have done towards this. Thank you.
Okay, thank you, Olga. Can you see the slides?
Yes.
Yes, okay. Okay, so this is actually a presentation on which is focused on synthetic videos. So there has been in the last few years a lot of attention on images and on deepfakes, but especially focused on faces, so like face swapping and facial reenactment. While now, since last year, we are seeing these incredible videos that are highly realistic and that can be easily generated using a short description. So I'm showing to you here some examples, so you can just write a few lines and generate a video in really a few minutes. These are examples from 3 different generators, Sora, Pika, and Runway ML. There are also others that I will show you later, and they are actually increasing every day. So, I mean, there are new upcoming generators with even better level of realism, or in terms even of richness of the content, which is always already these ones are incredible, but I mean they are keeping to improve even this stuff. So how can we detect this type of video? So first thing we have done was we have analyzed possible forensic artifacts of the videos. I mean, in the previous presentation, Christos has shown to you that images embed specific low-level invisible artifacts that are related to the generators, and these traces can be analyzed and extracted using a frequency analysis. So what we have done, we have analyzed videos, different videos also for these fully synthetic videos to check if also for these videos similar traces were present. And in particular here you can see the pipeline we applied. So the videos are actually denoised in order to remove the content of the scene and obtain a sort of noise residual. And then we analyze such noise residual, average them over time in the Fourier transform. We average them along different directions. So we consider both the spatial direction, but even the direction along the temporal direction, so different planes in our analysis. And I think you can already see here in this image, but I will show also in another slide, these peaks in the spatial domain and along the temporal dimensions. So you can see these strong peaks which are related to the upsampling operation that is embedded in the decoder of the generation pipeline. And this is interesting also because this upsampling operation is common to different generators. And here I'm showing to you actually these fingerprints for different type of generators, pyramid flow, Allegro and Nova, which is even a generator which is based on a different type of generation, not completely based on diffusion models, but on autoregressive models. So you can see that all of them have slightly different fingerprints, but they all present these peaks. And in particular, you can see that peaks along the temporal direction are more visible for some generators, less visible for others. And so what we noticed, of course, I mean, I also want to show you a comparison with real videos and highlight that real videos that we are presenting here on the left do not present such artifacts. And what is also interesting to see is that instead the real videos present peaks along the vertical and horizontal direction. And these peaks, so these peaks along the vertical and horizontal directions are related to the compression artifacts. So these are actually related to the video codec that causes such peaks because of the way the compression is carried out, which is block-based. And here you have these peaks along vertical and horizontal direction. Now, this synthetic data in this case are not compressed. And as I told you, of course, I mean, if we observe the data in this way, they are easily distinguishable. But what happens if we compress also synthetic data? So let's first start to see and highlight these artifacts related to compression, which are then not related to synthetic data. And I'm showing to you the artifacts here on the left related to the synthetic generators. They are highlighted in this green circles, while the peaks originated by compression and that are embedded in real videos are highlighted in these red boxes. And now here in the center, I will show the synthetic videos after compression, which is actually what naturally happens. I mean, a video is generated and then is uploaded on the web, and so it's actually compressed. And here you can see that also synthetic videos after compression present such artifacts. And the peaks that were previously present related to the synthetic generators are now not visible anymore. Still, you can see some artifacts here along the diagonal direction. So we thought, okay, so if we analyze compressed videos, we have to take care to push the detector to look at the right artifacts. Otherwise, it could confuse forensic artifacts related to the synthetic generation with the artifacts related to the codec used for compression. And so what we have done, we have, so first of all, the main observations are that the inconsistencies in the middle frequency content along the diagonal directions are robust to video codecs. And so what we propose is an augmentation strategy that replaces specific frequency bands and guide the model to exploit more relevant forensic clues. And in order to avoid polarizing on horizontal and vertical frequencies, where actually forensic artifacts related to compression overlap with the artifacts related to synthetic videos. So this was our idea. And what I also want to say is that this is also something more explainable. As Luca said in the previous presentation, it's important to explain what's happening and also show which are the artifacts related to synthetic generation. So we used the wavelet transform to decompose the signal into several frequency-related subbands. And here you can see an image and its wavelet transform, where what we do during augmentation is actually replacing low frequencies bands from real to fakes in order to avoid the detector to polarize, to focus on such traces. And when we do this, we also want that real and fake videos are perfectly aligned in terms of semantic content to avoid that there is a mismatch in terms of semantic content. This is actually related to what Christos has presented to you in the previous presentation, where we perfectly align real and synthetic generation by taking real videos and passing them through an autoencoder and generated like pseudo fakes using this strategy. And so overall, the augmentation strategy is applied is a weight-based augmentation strategies that pushes the model to learn frequency cues that distinguish real from fakes. And this is in order to test our approach, we both used publicly available datasets, but we also generated a dataset of 10,000 AI-generated videos. We did this because all the videos we found, the datasets we found online were quite old. So we wanted to collect some more recent generators that were able to generate videos with no clear visual artifacts. And here you can see the same prompt that were applied to generate synthetic videos from 7 different synthetic generators. So Sora, Flux, Nova, as I told you, I mean, which is like an autoregressive model. And we used, and in the selection of the text-to-video generation, we selected those that produced high resolution, high frame rate, and good results on a recent benchmark that was published last year at CVPR. So we actually selected only generators that could give very good visual results. And here I'm showing just some results that you can find more in our archive, where we compare with the state-of-the-art methods for synthetic video detection. Note that such state-of-the-art approaches even exploit the temporal direction, which is not currently done in our approach. Though, I mean, our approach is able to give better performance in terms of different metrics on 16 different generative models. And so we propose this weight-based training augmentation that promotes learning more discriminative frequency artifacts in order to distinguish real from synthetic content. And so we try to improve generalizability, more working. So our focus is more on the data. I didn't probably highlight that in all this analysis, we train on one single generator, while the other methods where we compared with were trained on multiple and different generators, and also had a very complex pipeline in terms of architecture. So we trained on one single generator, which is pyramid flow, and we didn't use it for test in order to avoid, of course, polarization. And so what we noted was that we were, in any case, able to obtain very good results, even if we exploited only artifacts along the spatial dimension, since we noted that the artifacts in the temporal domain disappear very soon after compression. And so our next step is to try to exploit the temporal domain in a way that we can extract also such forensic artifacts. Thank you. This is my presentation.
Great, Luisa. Thank you very much. Although ongoing work, we see that you already have done a lot of things towards this direction. I don't see any questions for this presentation. However, for this slot, we have one more presentation, which is video-based. It is a tool for AI-powered keyframe selection and enhancement, which Kostas will present to us. So I will leave the floor to Kostas to present, and if there are any questions also for Luisa's presentation at the end, you can add them at the Q&A section. Thank you, Kostas.
Okay, so good afternoon, everyone. I'm Kostas Apostolidis. I'm a research assistant from CERT. I will present the keyframe selection and enhancement service developed under the veraAI project. This is a tool that supports the verification procedure for videos. I will begin by outlining the problem we address, followed by a description of our own approach, how it operates. I will list the key technologies involved, and I will discuss the complete workflow and finally present the KSC service. Let's start with a problem definition. Let's see this video. So today's challenge goes beyond spotting deepfakes. We must also ask whether footage has been taken out of context or otherwise tampered with. So consider this clip claiming a Paris invasion. Clearly, the video is fabricated. An actual attack on Paris would be immediately covered by major international news outlets. Such an event would reach the public through verified channels long before appearing as an isolated tweet. Yet, the clip went viral, reaching over 2 million views, and was widely reshared without context. This is a 45-second CGI video, first appeared on March 11, 2022, when Ukraine's parliament tweeted under the caption, "Would the famous Eiffel Tower in Paris remain standing under relentless bombing of Russian troops? Today is Ukraine, tomorrow will be the whole of Europe." It was not commissioned by the Ukrainian government, rather a French producer and director created independently as a wake-up call for the Western publics to urge a public no-fly zone over Ukraine. As I said before, the clip went viral, over 2 million views, and was widely shared without context. Some posts even stripped the closing disclaimers, recasting it as evidence of a real attack. So when someone claims that the video is real and shares it, for example on Twitter, X, the most appropriate answer to ask is this video taken out of context? In fact, we use this very example, the 22 Paris bombing mockup, to validate our pipeline in 24 and 25 evaluation sessions, demonstrating how quickly our service, KSC, Keyframe Selection and Enhancement Service, can expose and debunk misleading narratives in real-world verification scenarios. So we understand that deepfake and synthetic videos are just one part of the problem. The media verification domain requires tools that go beyond deepfake detection to address broader manipulation techniques. Misinformation can also arise from other type of misleading attempts, such as cultural alteration, the use of original videos as a basis for manipulated content. For example, a real video that has been digitally altered to change its content, often by adding, removing, or modifying visual audio elements. For example, a politician's speech is edited to change their words, so change the actual content, making it appear as if they said something controversial. And the second type is contextual misuse. So videos presented out of context, a presentation of videos in a way that distorts the original meaning, intent. Which means a real video that's presented with misleading captions, timestamps, or contextual framing to support a false narrative. For example, a video of military exercises falsely claimed to show an ongoing invasion that may cause unnecessary panic. In the last category is also the video we saw of the Paris bombing mockup. Let's see our approach on this. So we devised a method to perform AI-powered keyframe selection and enhancement. We begin by finding critical frames in the video, thus reducing a long video to a number of images, the keyframes. Then the extracted keyframes can then be used as input for various other verification tools and subsequent analysis processes. Then we deploy deep learning methods, making it possible to glean useful clues from low quality images by making more visible the key parts. Of course, we do not claim perfection. This is a force multiplier, a tool to accelerate and scale the verification process. Now let's see how this works. Our pipeline begins with temporal fragmentation, segmenting the video into shots and subshots. Then we detect semantically meaningful key elements like faces and texts. And finally, we enhance these detected regions to reveal obscure details. Now let's briefly see the key technologies behind our AI-powered keyframe selection and enhancement pipeline. So we employ video fragmentation. Video fragmentation is a process of dividing a video into meaningful segments by detecting visual content changes, camera cuts, or significant content variations. Video fragmentation can also be seen as the process that organizes videos into structured and analyzable components. Through extensive experimentation in the field, we found that shot is a more intuitive concept for human understandings, whereas subshots are particularly useful for algorithmic analysis of the video, and video temporal segmentation to scenes is irrelevant for short videos. We employ video keyframe selection. Video keyframe selection refers to the process of identifying and extracting the most representative frames from a video to summarize its content while minimizing redundancy. And keyframes serve as fingerprints that can be compared across different videos. Based on experiments and professional feedback on video keyframe selection, particularly from journalists involved in media verification tasks, the consensus is that the more keyframes, the better. Of course, we aim to strike a balance, avoiding too many unnecessary keyframes while ensuring enough keyframes to capture the video's essence. But when uncertain, we discovered that prioritizing redundancy is the safer approach. We employ face detection. Face detection in videos involves identifying and locating human face across video frames. Recent models outperform human in challenging conditions, so this makes automated face detection both accurate and scalable. We employ text detection. Text detection in videos involves identifying and localizing text regions in video frames. And again, extracted text can be compared across different videos to check if the same embedded textual information appears elsewhere, which indicates possible recontextualization or content. Of course, again, recent advances in text detection have significantly improved the performance in detecting nonlinear text, making again recognition more robust across diverse real-world scenarios. Now, super resolution is the process of enhancing the resolution of an image or video frame to reveal previously obscure details. There are super resolution methods that are specifically designed for text region or faces. These consider task-specific features beyond that used in super resolution approaches, in general super resolution approaches. They offer readability in the case of text regions, of super resolution for text regions, and facial depth preservation in the cases of face super resolution. However, the process of face super resolution can sometimes introduce incorrect or even unrealistic facial features, also known as hallucination. We came across this actually, we were notified by test users. And we found that apart from choosing the right method, of course, moderate upscaling ratios work best in the context of media verification. Now let's dive into a breakdown of the workflow. I will outline each step and its purpose in the overall process. We begin, of course, with grouping visually very similar frames and process the least blurry of each group. As we discussed earlier, we temporarily segment the video to shots and subshots, and we select a representative frame for each subshot. So the next steps are conducted only on the representative frames of each snapshot. Since our goal is then to detect key elements that could provide valuable tools for verification, we focus primarily on faces and text as the main verification elements. Let's begin with the detection of faces. After detecting all faces in the representative frames of the shots, we group similar face elements by tracking the motion of the bounding boxes around each detection. We estimate the blurriness of each face element in the group and select the sharpest item of the group. We apply super resolution techniques to enhance the selected image. By selecting image, I mean the sharpest one of the group. Now, this strategy has two main advantages. First, since all the images in the group belong to the same person, applying super resolution only to the sharpest image ensures that we avoid unnecessary computational overhead, while still retaining all the important details without loss of information. And secondly, by choosing the most detailed image, we ensure that there are sufficient features for the super resolution to improve. We employ the same procedure for text regions. We group the text regions. We estimate the blurriness of each text region and select the sharpest one. And we apply the computational heavy super resolution process only to the selected item. Now let's briefly talk about the keyframe selection enhancement service. So we've encapsulated all the previously discussed technologies into a web service. The keyframe selection enhancement, a web service that automates keyframe selection and enhancement, helping other users quickly verify video authenticity. The service is web-based, requiring no installation, and seamlessly integrates into existing workflows, offering a much-needed simplicity. At this point, I should highlight that while machine learning methods are evaluated on standard benchmarking datasets in the research papers, we conduct additional testing to ensure real-world applicability. Specifically, we deployed multiple recent state-of-the-art methods, used in-house data, and measured their performance under identical hardware conditions. This approach provided a more practical assessment of their effectiveness beyond published benchmarks. And the key challenge was always selecting the most appropriate method, ensuring that we strike a right balance between the measured speed by us and the reported efficacy in the literature, reported by the authors of each method. So the KC service replaced the existing video fragmentation service within the verification plugin. Of course, when comparing the previous service to the newly developed system, we can see some interesting improvements, which we have already discussed. The thing is that the older video fragmentation service used in the plugin was highly optimized for speed and has already been adopted by a large number of users. So given this, the KC must maintain a comparable execution speed to ensure a seamless transition. As we discussed, our efforts were focused on optimizing performance by reducing redundancy, tracking motion, and selecting all the sharpest elements for enhancement. Going back to the detailed workflow we discussed earlier, we can understand that these two stages are planned for speeding up the analysis process. Our efforts ensure that the system provides real-time analysis. So you can see that the cases process is at maximum the 78% of the input's duration, on the input video's duration. As already discussed, the KC service is in the verification plugin. You can download the verification plugin as a Chrome extension from the link on the screen. And KC is also available as a standalone web interface. It is publicly available for testing and demonstration purposes, with some limitations applying to the video size and video file size and duration. You can visit the online standalone version, it's free, in the URL on the screen. And this is from my side. I will gladly answer any questions, if any.
Thank you, Costa. Very interesting presentation, very interesting tool. We had two very different approaches, one for synthetic videos and the other for real videos that are used out of context. I don't see any questions from the audience. Very quickly, I would like to ask if Louisa see that a technology such as the keyframe selection, which segments the video based on some rules that Kostas presented, do you think that this could help as pre-processing or
I
something?
think yes, I think yes, because along the temporal direction, the peaks are in specific positions. So keyframe selections would be really helpful. Yeah.
Thank you. So maybe a combination would help to contribute towards this direction. Okay, I will not ask any other questions because we are out of time, and I would like to introduce the last presentation for this session. It would be three partners, Chingy Song from University of Sheffield, Andrei Kare from Autotext, and Martin Hyben from Kinit. They will present us a different approach, not specifically trying to detect a specific separate item, individual item, or estimate or find some visual evidences, but a special temporal narrative detection. And I will give the floor to Chingy, who will start with the presentation.
Okay, thank you, Olga. So I hope you can see my screen. Right, so hello everyone. So my name is Xingyi, and as Olga already mentioned, this is joint work between, among University of Sheffield, Kinit, and Anton. So what we are trying to present here is called data-driven narrative temporal analysis. Just a bit background about temporal analysis. So the temporal analysis is typically studying how topic or document, their relationship changes across time. Just some typical questions we probably gonna ask in the temporal analysis. For example, when did the topic surface, and how long this topic last, and what are the previous topics and the topic after those topics. So the reason we address about data-driven temporal analysis is because the amount of information is impossible do it manually. Just example, this is a screenshot I took from the Press Gazette. When they monitoring how many kind of news media published every day across the UK. So those are the 8 mainstream UK medias. What you can see is each day those eight UK mainstream media already like published nearly like 4,000 articles, and Daily Mail itself like publish 1,600 stories daily. Consider if you want to do the temporal analysis over like a decade time, or even like 50 years or 70 years, it is just impossible to do it in manually. So this is kind of a general architecture about our system or our tool. So in the beginning, you have a data set, for example, the collection of the news articles across decades. These articles contains, of course, the text, title, everything you need. And next step, we will do feature extraction. Okay. So the feature extraction, including, for example, topics. I will give some a real example about topic extraction. And we have the topic hierarchy, and we will also group those documents into clusters, or group them based on the narratives. And we will do some narrative extraction and naming. And we can also extract the locations mentioned in the document. So you can do the spatial temporal analysis. And we will, together with the original text, we will index into a database. And you can conduct some kind of filtering based on like string filtering or time period filtering, or even based on those features. And the final step is based on the criteria in the filtering. You can visualize, conduct the temporal analysis. Okay, I will give you some like real example. As I said, this is joint work. So I will present the work from Sheffield part, and then I will pass to Martin and Andrew to present the work from Kimit and Anton. So in University of Sheffield, two things we are focused on. One is the topic extraction. So for each document, we will go through a large language model. So we train a large language model just do the topic extraction. And based on the embedding of this topic, so embedding is the kind of a numerical representation of represent the meaning of the topics. Okay, and then we will put them into a clustering method and group them in a hierarchical way. So that is the topic extraction. And in the same time, we will do the document relationship classification and to classify how related of each document. So, and then we index them, and we have the UI. So I will present the UI, but if anyone interested about the UI and API about the topic and the temporal analysis, we do have the tool that's available for you. But it's not publicly available right now. But anyone interested, you can email me, and I can arrange the access to those tools. Right. First of all, about the topics. So how these topics looks like. So those topics are extracted based on a benchmark data set. It's got 20 news group. Based on the 20 news group, so 20 news groups, they have like manually collect those news articles and also mail interactions and put them into 20 different topics. Of course, we are not using those human labeled topics. All of those are automatically generated. So, and what you can see here is an example of a topic hierarchy. For example, we have the root level topic called religious study, and we have a subtopic about the philosophy of the religion and religious movements. Of course, we have the leaf level topics about God, Israel, and Christianity. Here is another example. Again, we are not have fixed number of the hierarchy. It's all automatically decided. So here we only have two levels. The top level is computer networking, and we have the IP address, internet, and programming. So in our UI, of course, you can visualize the topic in a tree structure, and we have the circle represent the number of documents in that topic. And now move to the temporal analysis. This is kind of a demo, a recorded demo about the UI. So here is the kind of a topic level view, and each topic is represented by a stream. So the size of the stream represents the number of documents, like in that period mentioned about this topic. Of course, you can click the each of the topic, and you can see that this is the lower level sub level topics, and we have the connections, right? Just show how topics related to each other. So I will have another kind of a case study about COVID. So, but this is kind of a general overview about the topic temporal analysis. And here is the more granular view in the document level. So each of the dots represent a document, and of course we have the link between each document. So as I said, we have a classifier to classify how the relatedness of each document. Of course, you can adjust the threshold, right, about the relatedness. Okay, if you increase the threshold, of course, there will be less documents actually related to each other. You can see there are less documents. Again, we put them into an elastic index, so you can do basic kind of a keyword search. So, for example, if you put like typhoon related keywords, it will filter out the documents only related to your query, and you can conduct the the analysis only based on the keywords you selected. So I'm gonna fast forward a little bit. Of course, you can adjust the time span here, and it will show the documents only in that time span. As I said, we have the hierarchy of the topics. So you can filtering based on the topic. For example, you have top level topic about space exploration, and you can have the sub-level topic about the spacecraft launch. And you have the 3 articles in that topic. So probably can't see it, but the first document is talking about a spacecraft launch. And the last document is about the astronaut return. Obviously, you can see what's followed by a spacecraft launch. You can do this kind of a temporal analysis. I'm going to skip this one. And I will give you some case study about COVID misinformation. So we kind of conducted those temporal analysis based on the IFCN COVID misinformation data. And here is the top level, root level topic view. Again, it's showed in a stream graph. And you can see how those topics connect to each other. For example, we have the vaccine ingredients, and the vaccine ingredients linked to health and wellness, maybe linked to the medical breakthrough, this topic, and then maybe connect to other topics, including, for example, global health or linked to the global governance. And here is the interesting story about the in the document level. So, for example, if you spot a misinformation about like COVID vaccine contains HIV and SARS, and you're probably interested about like how this this misinformation coming from. So, based on the again IFCN data. So previously there is a misinformation about like COVID contain HIV insertions, and then it's mutated to COVID is a bioweapon mixing with SARS, and then there is another like misinformation. I combine those two, and like COVID vaccine contains HIV and SARS. And also here is another story about this vitamin C can cure COVID-19 and mutated becoming like vitamin C and lemon water prevent coronavirus. Yeah, here is more examples. For example, here is the dot about like the person lying in the street in China, and then there's a misinformation about China planning to cure coronavirus patients, and then in later there is another misinformation mutated like China seek court approval to cure 20,000 patients. Yeah, another example like Israel created a vaccine for coronavirus, and then mutated becoming like Israel plus USA come out with a vaccine. So yeah, in general, that is kind of our solution for the temporal analysis. Thank you for listening. Now I'm going to pass to Martin for the next session.
Yeah, thank you very much. I will share my screen as I cannot control the presentation. I hope you can see my screen. Okay, so let me start with a big graph. But don't worry, I won't go into much details. Please focus on, or let's focus on the input of the graph. So as you can see, there are two inputs. One is the corpus dataset that contains multi-claim dataset or media content library, which are basically the datasets of check-worthy claims, mainly collected from fact-check articles. And the other possible input is the user-provided text. So basically, Kinit is providing the central claim extraction tool, which allows us to take user provided text and extract the check-worthy claims from this text. So these basically two inputs gives us three possible input options. One would be just to basically take or compute the narrative hierarchy of the whole corpus dataset. This is useful for example, if you are looking for similar topics to the topic that you already have and you just want to search the corpus dataset for it. Another option would be to just basically analyze the user provided text and the Chegorty claims are basically the most important information from this text or from this content. But I think the most like practical solution is the combination of these two. So let's like imagine that you have some text from let's say a news article, and you want to extract these Chegorty claims or the most important information, and you want to put it into the context of the corpus dataset. And so all of these three options are possible with our pipeline. So let me go really quickly through the pipeline. So basically, what we do is apart from other steps, we do the initial clustering, which allows us to discover the macro clusters or the biggest, the most important clusters. And next, what we do is the conditional subclustering. So in case of really big clusters, they are discovered in the first step, we try to do a fine-grained clustering of these and split them into smaller clusters. And next, what we do is basically we do the visualization, and so the user can interactively like work with the results. So let's see a practical example. So as I said, there is some news article, let's say very recent one on attack on US bases by Iran. So what our Chegorty claim detector does, or it can extract the Chegorty claims. You can see that this is very dense information here, and only the last sentence is not Chegorty. And basically, we can combine it with the corpus dataset. I will show you. Sorry, this is. I will show you the real world scenario, real world demo here. So here you can see that this is our corpus dataset. This is specifically media content library. And you can see that there are like macro clusters immediately visible, but you can go into the hierarchy and you can discover micro clusters or smaller clusters, but also you can go up to each document, and you can basically get the information. What you can do is you can also filter. So let's for example filter only the documents that contain Olaf Scholz. You can see that it's in this area of the graph. I will not show today the basically interaction of user input with the corpus dataset, as it's outside of the scope of this presentation due to the time restrictions. But we are preparing the tool and Kinit that will be publicly available, and it will be available there. So stay tuned. And that's all from me. And I'm giving the floor to Andrei, who will continue with this part of the presentation.
Okay. Hello, everyone. I'll also try to be brief so we fit within the time. Our part of the system is also focused on discovering clusters of reused content across languages and across time. So the actual workflow that you can expect is you load some kind of corpus into the system. It calculates embedding vectors for all of the documents. It clusters them. Then it gives descriptive brief names to each cluster so they're easy to process and orient yourself. And then it includes a bunch of enrichments based around multilingual entity linking and event detection, and also things like the time span of the document. So we'll see more of that in a bit. And then it's all loaded into the database of known fakes, which exposes two ways to actually search through the data. One is the interactive UI, where we have a powerful search functionality, and another one is a chatbot, which is a more open-ended discussion. The chatbot uses the same access to the same data to answer your questions and is capable of redirecting you back to the UI. The focus in our case is to build not whole narratives, but rather smaller instances of data reuse that can be encountered in different contexts. So to that end, we've run both about a few 100,000 disinformation claims through the process, and also we're working with the same export from Meta and TikTok as the previous demos, and those have separately been clustered. Now, the goal is to have really specific clusters that have um, very similar documents, so you can kind of actually assume they're talking about the same topic, and you're searching for the right cluster for your needs or connections between existing clusters. I have two spreads here. On top you can see the disinformation claims from the database. So when working with 200,000 claims, they're reasonably unique. There's still quite a bit of overlap between languages, but this is on a log scale. So more than half of the disinformation claims are actually unique enough that they haven't been clustered. And then the vast majority of the clusters with more than one claim have 2, 3, 4, 5-ish, and then it really falls off very quickly with a very small tail of clusters that have 10 or more claims, which is essentially saying that there was some bit of disinformation that popped up multiple times across different countries or at different times and required writing new debunking articles over and over again. By comparison, in the bottom, we have the clustering over social media posts, and those are both fewer documents, so only about 10% the size of the claims, and also over a much smaller time scale. But we can see that there's much larger size clusters. So the way the system is supposed to work is if you've loaded in a data set that you want to analyze, it clusters, and you've clustered it, you can look at the big clusters to kind of get an idea of what the main discussions are. But if it's a social media post export, it is much smaller. Rather, the clusters are much bigger, so you can quickly go through the big clusters. Now, just to give you an idea of how the system works, this is the search interface I was talking about. So it gives you access to all the data. So let's say I'm looking at social media posts, and I want to see any that are talking about an earthquake. So I say they mention an earthquake. No, sorry, it's weird. Yeah, the worries of a live demo. Or California. So I can see there's a whole bunch of social media posts that have been clustered together. They're talking about an earthquake that happened in Northern California and supposedly it caused a tsunami. Now, since these are social media posts, they're not fact checked. So if I wanted to figure out whether anyone has looked at this, and since I know there was no tsunami in California in December, I assume someone probably looked at it and debunked it. But how popular was it? So if I decide to search for claims that they're talking about California and earthquakes, for example, I can see that it actually got debunked. And there are two instances. Here's one in Spanish, for example. But were there larger clusters of debunks here? Well, in the interest of time, yes, there are clusters of that. But to show you how the cluster visualization works, and how we can look at bigger topics, I'll actually show you something different. So I go to the cluster search, the European Commission as a concept that needs to be mentioned in the clusters, and I order them by size, and I see there are 217 clusters that talk about the European Commission in some meaningful way. And there are too many for me to read all at the same time, but I could go here and look at this visualization, which is basically telling me when they're active throughout time. So the earliest and latest document in them and what their time span is. And I can see some of them are running for several months or years. Some of them are quite brief, only happening within a month or maybe even a single day. So there's quite a bit of variability here. And if there's one particular cluster I want to look at, then it could be, say, I'm interested in the ban on car repairs for cars over 15 years old. If I go here, I can see there's a cluster where it was debunked in 6 languages, and there are 9 unique debunks published on the topic over the course of almost a year. These are the key concepts, unsurprisingly, vehicles recycling European Union, and this is the timeline of when the individual claims were debunked. And I could go to any of them. So we can see here, Polish, Greek, English, French, Bulgarian, so on. I could go to any of those documents to get more metadata on it, or I could follow it to the originally published source and get the actual initial source of the debunk. And finally, just very quickly, the chatbot gives you access to the same thing. So if you feel a little overwhelmed by all the search functionality, you could start by just asking the chatbot to do things for you, and it can also explain how it's doing things. So if I ask it, what are the 10 largest proto-narratives in social media posts in the database, for example, it would explain what it interprets my question to mean, how it's going to go and find it. I could go and get an explanation here, which it would show me the actual queries and tools it's using to get it, and then to summarize the results for me. So these are in the social media posts, they're the 10 largest ones. But none of these are actually disinformation. They're just the most discussed ones. But I noticed there were, earthquake posts. So I asked it, is there anything about earthquakes? And it does find a cluster of 29 social media posts talking about the tsunami in California. I asked it to find, follow back to other links. Are there any claim clusters talking about that? Which one is the most relevant? Who published a debunk on it? And it gives me one specific debunk by full fact, and it also can give me information on debunks on the same topic by other organizations as well. So that's very briefly and quickly how our system works. And this is connecting the clusters and finding connections and content reuse. And the goal here is to speed up analysis and discovery within large data sets.
Thank you, Andrei. Thank you, Tingy, Martin. Very quickly, because we have some questions at the Q&A. First question from Veronica Solopova. At the Tingy presentation, at the slide of COVID topic evolution, there were multiple times having global health and also one topic 937, and she would like to ask why this happened.
Yeah, so nice spotting. So as I mentioned, it's all automatically generated. So yeah, there is some kind of issue with the topic, like especially top level naming problem. So for example, three global health is due to the topic clustering is probably extremely similar. So they are named into one name. But and also 937 is topic 937. So that topic probably mixed up with different different topics. It's hard to like just name it automatically. So we just leave the topic number there. But we are trying to address those problems to duplicate and make the topic generation better. And also in the UI, I mean, eventually we're gonna open the UI for you. In the UI, we do have the feedback system, so you can make the move. You can drag and drop like and rename the topics into like different parts of trees. So we will use those feedback to train our model to make it more sound in the topic generation in the future.
Thank you, Jingyi. There is also one more question about you. Did you find hints or evidence that the presented narrative analysis can or can't be used to detect new misinformation narratives published in the future?
So, I mean, it's possible. I mean, to say it's just it can't like. So the tool itself is just kind of trying to extract the topics and generate the relationship between topics and between documents. So we could look at the topic trends in the past, and if there is a kind of new trend of topics similar to the past, yeah, we will probably able to use that as an indication to predict the future misinformation. But that is not the intention for this too, but possibly.
Thank you. A question which I guess is very quick about TikTok data, how they come. Do we have a research API? I think this is for Andrei.
Well, we all use the same export. It's provided by one of the partners in the Vera project. None of our three organizations have direct access to the TikTok API, but our partner does. And we had a one-time export just to demonstrate functionality.
Thank you, Andrei. And last but not least, is there a way of comparing the graphs of different corporal communities, and if there are plans to make parts of the code base available? I'm not sure to who to direct this question, so feel free.
I can briefly answer this question, Martin and Andrei. If there's something you need to add, just feel free to jump in. So what we plan is we will have a kind of a proto allows to upload your own corpus. So obviously the graph were generated. The graph is generated by according to how you filter set up the filters, right? For example, the topics or keywords or time span, and you can upload different corpus. You can upload different corpus to generate a graph, and you can compare those two graphs. So that's something we plan to do. And also about the code, yes, we're gonna open source the all the code. But not right now, because we are still kind of fixing some kind of a algorithm issue, including the one some of you spotted, like the repeated topic names. Once we fix off those, it will be open source.
Yeah, I will join. So do we also plan to publish the code as a part of our publication that is currently being prepared? So yeah.
Great, thank you everyone. We are a bit late, but I would ask just to stay 2 more minutes here so we can properly close. I hope you see my screen. So you can discover more about Vera project at our website. We will also upload the presentations from today and also the session of last week. We will also share the video recording, so if you want to have a look again or remind something, If you have any questions or you want to ask something, feel free to contact us. For the research, you can join our Zenodo community where all our publications are available and you can download. And again, if you have any questions, you can get in contact. You can follow us on Blue Sky, where our dissemination manager, who moderated the last session, Jochen, do a very good job sharing all the activities that we are doing. And of course, in our website, you can see all the material, all the research, all the information that you would like to know about our project. Once again, thank you very much for joining this session. We really appreciate that you spend your time to connect and see our research. And have a nice day. Thank you very much, everyone. And also a big thank to the presenter. Bye, everyone.